Next we see the exercise set 3.4. We are not going to complete it in this video itself. We will solve the first 4, and in each one we have a trigonometric equation for which we have to find the general solution and also the principal solutions. The first one is tan x equals square root of 3. We will first find the general solution and then using it we will find the principal solutions. We have tan x equals root 3, which is also tan pi over 3 radians, or in degrees it's 60 degrees. So from this you can directly write the general solution. Hence, the general solution is x equals n pi plus the angle, where n is an integer. For the principal solutions, our x should be non-negative. X should be greater than or equal to 0 and should be less than, strictly less than 2 pi. For principal solution, this is the condition. Obviously, the principal solutions are also going to be solutions after all, so they will look like this. Now what we will do, we will substitute this expression for x here and then solve these inequalities to figure out those n for which these inequalities will be true, and they will be the principal solutions. I mean not the n's but the x's corresponding to those n's. N pi plus pi over 3 less than 2 pi. One simplification you can do here is that you can divide throughout by pi. Since pi is a positive real number, that will not flip the inequalities. The inequalities will maintain their direction, and doing so you will get this. And then you subtract 1 over 3 from the 3 terms. The middle one becomes n, and the rightmost one becomes 2 minus 1 over 3. Six minus 1 is 5. 5 divided by 3. Note that I am going on using double implication instead of single implication, because I want to know that if x satisfies these inequalities, then what happens to n. That's how I figure out that n has to satisfy these inequalities, and now I will find n. Using these inequalities and the fact that n is an integer, I will find n, but then I will also have to go back from those n and see that yes, if n has these values, then the corresponding x's really satisfy these inequalities. That's why I am using double implication. But be careful when you do this now. This is no longer simply this. So it's not that you just have to get these inequalities from these inequalities, but you should know that you can actually go back. Here of course you can go back because x is just this. So here there is no problem. But what about this step? What I just said now is that you divide throughout by pi. That's fine. That will get us these inequalities. But can we go back from these inequalities to the ones above? Yes, we have to multiply throughout by pi. That also is possible. I mean, of course, you can multiply by pi, but because pi is positive, so here also, if you go from these inequalities to the ones above them, again the inequalities do not get flipped and you get the ones above. And that's how the other steps can also be justified. Sometimes double implication cannot be used. You can go in only one direction, but you cannot go back. So you have to be careful actually. It's not that you simply go on blindly putting these things. Since, or let me just continue. Keeping in mind that n is an integer, what should the possible values of n be here? Minus 1 lies to the left of minus 1 over 3 because it's less than minus 1 over 3. So n cannot be minus 1. N however can be 0. N can be 0. Any other value? N can be 1 because 1 is actually less than 5 over 3. Why? Because 3 is less than 5. Can n be 2? No. Because if you forcefully suppose that 2 is less than 5 over 3, multiplying throughout both sides by 3 will get you 6 less than 5, which is not true. So these are the two values of n. So if n is an integer and n satisfies these inequalities, then n must be either 0 or 1. But can we go back from these values to this? Yeah, of course. If n is 0, then for that n these inequalities are true, and so is the case if n is 1. So these are precisely the values of n that will make x lie between 0 and 2 pi in this manner. Thus, the principal solutions are the one that you obtain by putting n equal to 0, then x becomes pi over 3. And the other one when you put n equal to 1, which is pi plus pi over 3, which is 4 pi over 3. These are the only solutions among the infinitely many solutions that satisfy these inequalities. So, by definition, they are principal solutions. Next, number 2. Number 2 is secant x equal to 2. Now that we have seen the process of finding principal solutions, for this one we do not need again all these explanations, we can just solve the problem. Secant x is 2 if and only if cos x is 1 over 2. And what is 1 over 2? Let me write here itself. In degrees, which angle gives, which angle has its cosine equal to 1 over 2? 60 degrees. In radian, that is pi over 3. So x is recall the general solution for this type of equations: 2n pi plus or minus pi over 3, where n is an integer. So here actually there are two types of solutions. Some of them have the form 2n pi plus pi over 3, and some of them have the form 2n pi minus pi over 3. So that's the general solution. And you can, because here we simply directly wrote this, you can continue this, which is the general solution. For principal solution, again same inequalities. Two n pi plus or minus pi over 3 less than 2 pi. For the sake of simplicity and so that we do not make any mistakes, I am going to write two things here, depending on which one we are choosing. Less than 2 pi or minus pi over 3 less than 2 pi. Now we continue working on both of these sets of inequalities. Divide by pi, that gives you 2n plus 1 over 3 less than 2, or, see, I have already made a mistake. It seems like a minor thing, but still it's a mistake because I am losing the possibility of equality. You have to be careful with these things. Or 2n minus 1 over 3 less than 2. Okay. In the first set of inequalities, we subtract 1 over 3 from all the terms, as before. Less than 2n, or, and here we add minus 1 over 3 less than or equal to 2n less than or equal to 5 over 3, or 1 over 3 less than or equal to 2n less than or equal to 7 over 3. Less than 7 over 3, not equal to. But we want n, so now we divide throughout by 2. That gives us minus 1 over 6 less than or equal to n less than 5 over 6, or here also 1 over 6 less than or equal to n less than or equal to 7 over 6. So what type of n can we expect from the first set of inequalities? Just like before that one, the previous one, n cannot be minus 1 because this is already greater than minus 1. N can be 0 however. Can n be 1? No, because 5 divided by 6 is less than 1. So here only one value of n is possible, which is 0. N equal to 0, or what do we get from this one? This is also similar. 0, n cannot be 0 because 0 already lies to the left of 1 over 6. N can be 1, but n cannot be 2, because if n is 2, then 12 will be less than 7, which is false. So here also we end up getting two values, but from two sets of inequalities. Hence, the principal solutions are, but be careful, which one you will put where, that you have to really figure that out carefully. N equal to 0 is coming from where? From the first set of inequalities. And for the first set of inequalities, we have this expression for, well, not this expression because this is the general one, sorry, not this one, but this one. So you have to substitute n equal to 0 here, and that gets you pi over 3. And the n equal to 1, that option comes from solving this second set of inequalities. So in this expression you have to put n equal to 1, and that gives you 2 pi minus pi over 3. That means 6 pi minus pi if you take LCM and do the usual stuff. 5 pi divided by 3. So these are the two principal solutions in this case. Next, number 3, cot x equal to minus square root of 3. Presence of a negative value will, it will not be a standard angle. We will have to find it out. We have cot x equal to minus root 3, which is the same as tan x equal to minus 1 over root 3. Let us just keep the minus sign as it is. What is 1 over root 3? Tan 30 degree, or in radians, that is pi over 6. Now let me write in place of this something else. Tan pi minus tan pi over 6 divided by 1 plus tan pi over 6. Is it really equal to this? Yes, because tan pi is 0, so the numerator is minus tan pi over 6 and the denominator is 1, that is why. but this is in a standard form. This is tan pi minus pi over 6. Also note carefully that none of the two angles is an odd integer multiple of pi over 2. This is not even a multiple of, this is not even an integer multiple of pi over 2, it is pi over 6. This is 1/3 of pi over 2. 1/3, 1 over 3 is not an integer. And this is 2 times pi over 2, which is an even multiple of pi over 2. And that is why we are able to use the formula for tan a minus b. Tan x equal to tan 5 pi over 6. Now we can write the general solution, because this equation is equivalent to that. Equivalent, really equivalent means if this is true, then this is true. That you get from the forward implications. Also, if this is true, then this is also true. For that, you have the backward implications. Hence, the general solution is x equal to n pi plus 5 pi over 6, where n is an integer. Now we find principal solution. For principal solution, this is the requirement. That means n pi plus 5 pi over 6 less than 2 pi. Again, same technique, divide throughout by pi. That simplifies things. Then isolate n by subtracting 5 over 6 from all the terms. Minus 5 over 6 less than or equal to n. If you take LCM and then do calculation, you get 6 times 2 is 12, 12 minus 5 is 7. Okay. Now what type of integers n satisfy these inequalities? N cannot be minus 1 because this lies to the right of minus 1, it is greater than minus 1. N can be 0 and n can be 1 because 7 is greater than 6. So 1 is less than 7 over 6, but n cannot be 2 because 12 is not less than 7. And that is why here also n is either 0 or 1. So the principal solutions are, putting n equal to 0 gives you just this angle 5 pi over 6, and putting n equal to 1 gives you this, which is 11 pi over 6. And then there is one more. Here also there is a negative value, so angle won't be standard. cosecant x equal to minus 2. Let me just digress a little bit here. Let me say a little bit about this notation. This name, although the function is cosecant, this name that has been assigned to the function, that we write this when we talk about this function, is an old notation. It's not used anymore. The one which is used instead is CSC. But of course, because everything about this education system is old and outdated, you will continue to see this thing. Elsewhere, you will see CSC. Oh, and one more thing. On your exam paper, do not write CSC. Otherwise, for that also, mark may be reduced. You will be correct, but people don't know that here. So, taking reciprocals on both sides, we get sin x. Luckily, the more usual ones, sin, cos, they are just SIN and COS. So, which angle gives you 1 over 2 sine 30 degree, or in radians, that is pi over 6. And again, here we have to adjust things. How about sine pi plus pi over 6? This is not an arbitrary choice. Recall that sine of an acute angle, of course, this positive, any trigonometric function value for an acute angle is positive. But when it goes beyond 90 degree, but still in the second quadrant, sine is still positive, because sine is the y coordinate of that point. You know what I am talking about. But as you go to the third quadrant, y goes below the x axis and it becomes negative. That's why I am thinking of adding pi to this, so that this angle lies in the third quadrant. And now we have to see, do we really get this? Let us mentally check this. What will this expansion be? Sin pi cos pi over 6, and that term will vanish because sin pi is 0, plus cos pi sin pi over 6. Cos pi is minus 1, sin pi over 6, that means minus sin pi over 6. Yes. So this will be 7 pi over 6. So now we can write the general solution. Hence, there are so many problems with everything we do over here. The syllabus is unnecessarily long. Things are not well organized. There are gaps. You won't really get what you want if you really go for understanding these things, even at this level. Plus, the ultimate goal is getting marks in your exam, marks on the exam paper. Examinations are the ultimate goal. So how can you even hope or try to understand things? There is no time. You have to complete the syllabus in whatever course you are enrolled. You have to complete the syllabus by hook or by crook, and you just have to cram the things and write on the exam paper and then forget without even understanding, because there is no time. It's not your fault, it's the entire system's fault. What this does is that it encourages mediocrity, and that's what is happening with us, including me. Hence the general solution is, so what was the general solution for this type of equation? N pi plus, there was this thing, minus 1 to the power n times the angle, and where n is an integer. You think I know mathematics? I don't know I don't know anything. All these things, these are just, or whatever else I do, they are just rudimentary things. The people who really know some particular area of mathematics, if you meet them now, you will really feel that yes, this is something special. That is on another level. But because of mediocrity, it seems like I know many things. We have set the bar very low, and now we have to find principal solutions. For principal solutions, we have our usual inequalities, and then we use this expression, and here immediately there will be, I mean, you cannot just simply go on working on this singularly. You have to consider two cases separately, because you have minus 1 to the power n, that's why. Depending on the parity of n, whether n is even or odd, you actually here also, just like that cosine case, you will be getting two cases. Let us first consider the case where n is odd. Zero less than or equal to n pi, of course, is just n pi, but if n is odd, this is minus 1 minus 7 pi over 6 less than 2 pi. With that, you add this condition, if n is odd, and then what happens when n is even? In that case, we get plus. If n is even. Keep in mind that these conditions will continue to be with these inequalities and will affect your n when you finally are in a position of finding or saying what your n is. Okay, so divide throughout by pi, that gives us 0 less than or equal to n minus 7 over 6 less than 2 if n is odd. Don't be lazy, continue to write these things. Or less than 2 if n is even. Okay, so for the first set of inequalities, we add throughout we add 7 over 6. n less than 2 plus 7 over 6 if n is, I hope I have not switched the order, odd first then even, or here you have to subtract 7 over 6. If n is even. Alright, so the first set of inequalities becomes 12 plus 7 is 19 divided by 6 if n is odd, and here minus 7 over 6 less than or equal to n less than 12 minus 7, so that is 5 divided by 6 if n is even. Alright, now momentarily let's just forget that here n is odd. Let's just think of which integers lie in this region. 7 divided by 6 is slightly greater than 1. So n cannot be 1 because 7 over 6 has already exceeded 1. Can n be 2? Yes, because 7 over 6, since it's greater than 1 but at the same time it's less than 2. Similarly, 2 is less than 19 over 6. If you cannot immediately see how, you just note that 12 is greater than 7. So divide both sides by 6, you get 7 divided by 6 is less than 2. Again, 12 is less than 19, so divide both sides by 6, you get this inequality with 2 in place of n. That is why n can be 2, but n cannot be 2 because n is odd. What about 3? So we have to look for other options for n. It may happen, not in this case, but somewhere it may happen that no n eventually satisfies the inequalities and at the same time it's odd. Then this part will not give you anything. That's not the case here, because luckily the 3 option for n, it satisfies everything. 3 is odd, but at the same time 18 is greater than 7, so dividing both sides by 6 you get 7 over 6 less than 3, and 18 is less than 19 also. So 3 is less than 19 divided by 6. And that is why, in spite of these inequalities giving us 2 options, 2 and 3, because of this extra condition, n can only be 3 in this case. Or what about this? Minus 1 is an option here. Note that because 7 divided by 6 is greater than 1, so minus 7 divided by 6 is less than minus 1. So you can take n equal to minus 1, but at the same time you cannot take. For these inequalities that's okay, but n needs to be even here. Can we take n equal to 0? Yes, of course we can take n equal to 0 here, and 0 is also even. But the inequalities themselves do not hold any other option, they do not keep any other option for us. We cannot take n equal to 1 because 5 over 6 is already less than 1. So these inequalities combined with this condition gives you n equal to 0. Okay. So accordingly we are now going to get 2 solutions, 2 principal solutions. So let me write from here. The principal solutions are, because originally you had only one formula for the general solution, there itself you can put these two values. You do not have to separately take into account which one represents the even case, which one represents the odd case. Let's put n equal to 0 first. In fact, let's write like this. N pi, the beginning was like that, so 0 pi plus minus 1 to the power 0 times, what was the angle? I forgot, 7 pi over 6. Okay, so that is just 7 pi over 6. And you put n equal to 3. 3 pi plus minus 1 cube times 7 pi over 6, or 3 pi minus 7 pi over 6, or 18 pi minus 7 pi over 6, or 11 pi over 6. Yes, one of the particular solutions is 7 pi over 6 and the other one is 11 pi over 6. So this is how you can first find the general solution, and then using that you can find principal solution, not particular solution. There is something called particular solution when you will study differential equations in second year. There you will see this thing. So I mistakenly keep saying particular solution, principal solution. So that's just it for tonight. Tomorrow we have topology, because last week I think we did differential equations. So tomorrow we are going to again go back to topology. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.